In section 3.3, we're going to be looking at increasing and decreasing functions and something super important that we're going to be doing quite a bit with this first derivative test. And so before we kind of get into that, we want to kind of review what we already know about increasing and decreasing functions from some previous courses. And so first let's look at this. Increasing and decreasing functions, we're talking about an x1 and x2 that are in the interval. So if I have an increasing function, that would mean that x1 is less than x2. So your x's are getting larger. Then f of x1 is less than f of x2. So your y values are getting larger. Also meaning that you have a positive slope. Thus, think about your calculus, positive derivative. And so you can look at a graph and see if it's increasing, but I want to clearly define this, and so that you can look at it and go, okay, by the definition I can see that, because we're not always given the luxury of a graph. And so we understand that if this is x1 and this is x2, that here at f of x1, and let's put one up here, this would be f of x2, that would be a graphically increasing function, but the mechanics or definitions behind it would be as your x's are increasing, your y's are increasing as well. And so on decreasing, if you have x1 is less than x2, so as your x's are going up, then the reverse of that, f of x1 is greater than f of x2 because it's going downward. So again, we're talking about negative slope. Therefore, calculus, we're talking about a negative derivative. So you can't forget everything that we did with derivatives because it's still coming into play here. So if I had x1 and x2, then that would mean I have something like this, and this would be your f of x1, and this would be your f of x2. Just as you're going left to right, that function is going downward. Now, if we look at our constant function by definition, that would mean that we have x1 is less than x2, but then as we do our y's, that f of x1 is equal to f of x2. I mean, we defined increasing, we defined decreasing, why not define constant? But reminder, that is where your slope is 0, or calculus-wise, that's where f prime of x is 0, something we've been using a lot lately. So that would mean right here at x1, and then here is x2, and then this would be your f of x1 and your f of x2. And it's just your constant function or your horizontal line. No big deal. We all get this. We all get that increasing, decreasing. I just wanted to define it and look at what does it mean calculus-wise, especially looking at those slopes. So if I have an example here of find the intervals on which f is increasing and decreasing for the function, here's what we need to do to find where it's increasing, decreasing, because I have no doubt that you're a smart individual and you can look at a graph version of this and you can say, oh, it's increasing or decreasing here. And you've done that already in this course and in pre-calc, college algebra, etc. So let's look at it from the mechanics of it. Let's look at the equation and see how we can figure it out just by looking at the equation. And so the first thing we're going to do, we're going to write some steps. So the first thing you're going to do is you're going to, surprise, surprise, take the derivative. So you're going to look at that derivative. So let's just go ahead and find f prime of x. The derivative would be 3x squared minus 3x. You bring that 2 down, multiply it by the 3 halves, the 2's cancel, and you just get 3x. After you take your derivative, you're then going to, part 2, find the critical numbers. We've already been finding critical numbers in this chapter so far, and we've worked with them a little bit, but now we're going to work with them even more. So just as a reminder, when you're looking at your critical numbers, that is f prime of x is equal to 0, or f prime of x doesn't exist. Remember, that was our two situations. You can go back into your previous sections and relook at that if you need a reminder. And so I'm going to take first this 3x squared minus 3x, and I'm going to set it equal to 0. So I'm going to look at the situation of first the derivative being equal to 0. Now in the case of this function, there isn't anywhere that it doesn't exist. 3x squared minus 3x, no big deal. Even our x cubed, cubic or quadratic functions, it's very continuous. It's a smooth polynomial function. There's no really problem areas for it. So if I'm looking at that derivative stay equals 0, I'm going to factor. So I take out the GCF of 3x. That leaves me with x minus 1 equal to 0. Then, now that I have my 0 property, I can say 3x is equal to 0, which gives me x to be 0. X minus 1 is equal to 0, which gives me x to be 1. And then those two values right there are my critical numbers. Now, I'm not done with it yet because my goal was to figure out where this thing was increasing or decreasing. So now here comes into the new part that we need to do. So let me scroll down here. So what you're going to do is we're going to take those critical numbers and we're going to do some testing of them. So part 3, we are going to test the intervals around the critical numbers and we're going to be plugging them into the f prime of x. And that's new. In previous sections, we were plugging into the original function. So make sure that you pay attention to that part right there, that we are plugging into f prime of x as we are doing this. So I'm going to pull this up a little bit here. And so remember, our derivative, just so we can see it here on the screen, is 3x squared minus 3x. And what we're going to do is we're going to draw a number line. Taking it back to middle school days, we're going to draw a number line. We're going to plot on our number line our critical numbers. Now remember up here, our critical numbers were 0 and 1. So on this, I'm going to put a space for 0. I'm going to put a space for 1. Not x, 1. So I'm going to put a space for 1. And then what I'm going to do is I'm going to test these regions. And so what I want to do is I am not looking at 0 and 1. We already know that those derivatives are 0, so there's no sense for us to plug in. But what we're going to do is we're going to pick a value that's in each of these 3 regions that I've kind of marked off here using our critical numbers as boundaries. And we're going to see what is going on as we plug into f prime of x. So here's what I'm doing. I'm going to pick a value first in this region that is over here between negative infinity and 0, and be easy on yourself. Pick something that's very easy to compute or to evaluate at. And so I'm going to pick a value such as, and again, we're using our f prime of x equal to 3x squared minus 3x. I'm plugging into this. So I'm going to say f prime of, and I'm going to evaluate at negative 1. That's a really easy value that's over here to the left of 0. So I just plug it into my derivative. Remember, we're plugging it into this function here. We're not plugging it back into the original. A little change of pace from earlier sections. So it gives me 3 times negative 1 squared minus 3 times negative 1. Grab your handy dandy calculator, compute that out. That gives me a 6. Now remember, I am plugging into the derivative. So this is f prime of negative 1 gives me a value of 6. So that means the slope at negative 1 is 6, thus it's positive. So I'm not concerned with the fact that its numerical value is 6. I'm concerned with the fact that it is positive over here. And so that means over here in this region, I'm going to have positive slopes. We already know once it gets to 0, from our critical numbers up here of setting a derivative equal to 0, that that's where a horizontal tangent would be created. So then our next step is we are going to pick a value between 0 and 1 so that we can figure out what the slope is between 0 and 1. So I'm going to pick you can pick any value. I'm going to choose 1/2. That sounds like a good one. I'm plugging it into the derivative. And so I'm saying, what is the slope at 1/2? I'm going to plug into my calculator just like that, and that gives me -3/4. So again, I'm not concerned with the fact that it's -3/4. I'm more concerned with the fact of I'm plugging into the derivative, and it gave me a negative. So therefore, between 0 and 1, I'm expecting it to have a negative slope. And then lastly, what we're going to do is we are going to plug in, excuse me, let me change that around. We're going to plug into this region over here and say, okay, let me pick a value greater than 1. Notice I'm not plugging in 1 and 0. Greater than 1, and make it easy on yourself what you're picking there. And so I'm going to say f prime of, I just chose 2, 3 times 2 squared minus 3 times 2 is equal to, calculator, that gives me 6. Again, 6, cool, but it's positive, so I'm getting a positive slope over here. So now that I have created this number line, remember, and we were looking at the derivative, this shows me the slopes that I'm needing. So therefore, we can look at it and say, look, it's increasing right here, it's decreasing right here, it's increasing over here. So instead of looking at tables that we did in previous section, go, oh, that's the highest point, that's the lowest point, we're looking at this going, what are the slopes? What is it doing from -infinity to 0? What is it doing from positive infinity over to this 1? Then we can tell you where it is increasing and decreasing. And so I say, okay, well, just kind of looking at my arrows here, I could say, okay, we are increasing, and we're going to write this in interval notation. It is increasing, you can see from all over this region here, so that would be -infinity to 0, union with, over here, it's increasing. And so that would be from 1 to positive infinity. Where is this function decreasing? And that would be just right here in the middle. Right here in the middle. And so I could write that, and I could say that's from 0 to 1. So now we don't need that crutch of a graph to see where it's increasing, decreasing. We're going to take our derivative, set it equal to 0, and find our critical numbers. Those critical numbers create boundaries so that we could test values, like we were doing right here with our derivative, to figure out what the slope is in those areas. And then based off the slope in these areas here, we can figure out where is it increasing, where is it decreasing, and create those intervals. So we're just kind of building and putting together a lot of knowledge that we've already been doing. So this is a really nice example. Let's just kind of keep moving forward here in 3.3. And this leads us into something called the first derivative test. Now, the first derivative test is really nice. It makes it easy to locate extrema. You know, we don't have to draw a table. We don't have to look at graph. And so as we're looking at this first derivative test, we can kind of identify some things. It says, if f prime of x changes from a negative to a positive at c, and remember the slope negative, that means going downward, and then to a positive going upward, then f has a local maximum because you went decreasing to increasing, so that creates that c value, or that critical number, is a local maximum. Excuse me, I got those numbers wrong there, or letters wrong there. Let me correct this. This is a local minimum, because we can see if we're going down and then we're going up, that's going to create a value right here. There's your decreasing, here's your increasing, and there's your minimum. I got those two definitions switched. Sorry about that. And then you're going to say, okay, well, if f prime of x changes from a positive to a negative, we can see then that value at c right there is going to create for us, let me adjust that, a maximum. And then if f prime of x doesn't change signs, then there is no local minimum or maximum. And this brings in a new vocabulary word for us, and that would be strictly monotonic. And that's if it is increasing or decreasing the entire interval. And let me show you what that one would look like. It would be something like this. You can see that it's increasing here and increasing here, but they just have different speeds of increasing, or something like this. This is decreasing the whole way, but there is some change of pace in there, but there is no critical numbers that are occurring. And so again, that would be if your f prime of x doesn't change signs. And as we're looking at these changing of signs that we're looking at here, this is going to go back to when we were doing our interval testing and looking at that number line. So you're going to see some consistency in the processes that we are doing. So let's work with an example and see what we can do with it. Here's our example. Applying the first derivative test. It says find the relative extrema of the function. And so let's look at this and see what we can do. So first thing we need to check is this thing, so let me make notes of this. So let's check first, is this thing continuous? Well, 1/2 x minus sine x, yes, this thing is going to be continuous. Is this thing differentiable? Yes, we don't have any issues with the derivatives of this. And notice this is on the interval from 0 to 2 pi. We do want to remember those constraints as we move forward. So the next thing we're going to do is part 2. We're going to find the critical numbers. Okay, so in order to find our critical numbers, we've been doing this already a few times, we're going to find our derivative. So our derivative of 1/2 x minus sine x, because this is our original function, we want to find the derivative of it, would be 1/2 minus cosine x. Hopefully you're doing a lot better with those derivatives. We're going to take that and set it equal to 0 and solve. And so I'm going to move my cosine x over. That gives me 1/2 equal to cosine x. And then in relation to your unit circle, your trig circle, we know that cosine x is equal to 1/2 at x equal to pi over 3 and x equal to 5 pi over 3. So as we start to work with these critical numbers, we need to remember that this was restrained between 0 and 2 pi. So I'm going to take my number line and I'm going to stop at 0 and 2 pi. I'm not going to do anything less than 0. I'm not going to do anything more than 0. We're just going to be looking between these two. And the critical numbers we found were at pi over 3 and 5 pi over 3. So these are going to be my boundaries. And as I work through this, I'm just going to check values on the left and right of it, but I'm not going to go bigger than 0, or smaller than 0 or bigger than 2 pi. So 2, I found my critical numbers. Those were my pi over 3 and 5 pi over 3. So step 3, if you like a process, you want to test points in the f prime of x. So again, you're putting values into your derivative. Make sure you're plugging into the right equation because we're looking at slopes here. We're trying to find increasing, decreasing. So I'm going to pick some nice values. I'm probably going to pick values for my trig circle. And so I'm going to say, what is f prime of pi over 4? And so that would be 1/2 minus cosine of pi over 4, and that's on your unit circle. And so then that gives me 1/2 minus the square root of 2 over 2, which is roughly just negative 0.207. And I'm okay with just grabbing that decimal because, again, I'm not concerned with the 0.207. I'm concerned with this negative right here. So that means that between 0 and pi over 3, that's going to be a negative slope. So then if I come down here and test another value, let's look at f prime of pi. So that would be 1/2 minus cosine of pi. You know, you should be using your unit circle with this, but if you are using your scientific calculator, make sure it is in radians in order to get the correct value. And so then that gives me equal to 1/2 minus negative 1, which is equal to 3 over 2. And again, I'm just concerned that that's positive, so I can come up here and I can say, okay, well, it's going to be positive slope in between those two. And then I'm going to pick something right over here in this last interval between 5 pi over 3 and 2 pi. And so I'm going to come down here and let's pick f prime of, let's do 7 pi over 4. So it gives me 1/2 minus cosine of 7 pi over 4, which gives me 1/2 minus the square root of 2 over 2, which we've already seen that to be negative 0.207. So again, I'm just concerned about this thing being negative right here. So this tells me that this is a negative slope. Now you can't just assume things are going to go negative, positive, negative, or anything like that, because as you saw in our previous definitions, sometimes if you don't have a sign change, then it becomes strictly monotonic, and so you might have a different situation arise. Or if you notice some weird things happening as you draw this number line up here, you might go, you know what, did I find the right critical numbers? And you might be having the wrong boundaries, so you might be having funny things happen. So now when I look at this, I go, oh look, it's going down right here, it's going up right here, it's going down right here. So you can see some information has arisen. And so if I come over here and write what we have found, I would say it is increasing on the interval from pi over 3 to 5 pi over 3. It is decreasing on the interval from 0 to pi over 3. Union with 5 pi over 3 to 2 pi. And then furthermore, if I'm looking at this and I want to find the extrema of this function, you can see that it's creating a minimum right here at that critical value. It's creating a maximum over here, just kind of connecting those. So I would say that there is a minimum. Can't spell minimum. Let's see, minimum at pi over 3, and that there is a maximum at 5 pi over 3. Now those are just my x values of where they occur. If I want to find the ordered pair that goes with that, I just need to take these values here, and because I'm looking for placement, I'll go back and I'll plug them into the original function, and then from that original function, I'll be able to tell what the y value is that goes with that. And so really neat information here. And if I just kind of scroll back to what we were doing here, I took this function on the interval, we took the derivative, we set it equal to 0 and solved, and we found two values. And then by using our interval here, we're able to see where is it increasing, where is it decreasing, and then we're also able to figure out its minimums and maximums. And so really, after you take the derivative and set it equal to 0, the rest of it is using your number line, analyzing, and evaluating. And so then we're able to get this information or data and say, okay, here's our increasing, here's our decreasing, here's our minimum, here's our maximum. So a problem such like this is a really great test problem. You can tell it does take a little bit of work. You do have to use a calculator more in this chapter because we are evaluating, but you have to make sure you're flipping from evaluating your derivative or you're evaluating your function. So if you need any additional help on this as you're working through the homework, please reach out to me. Otherwise, we can address questions together once you've all kind of looked at it. So I hope this helps in looking at 3.3. Feel free to Canvas message me if you have any questions, comments, or concerns.